panelists. Now I see 5. So the idea is that all panelists will introduce themselves briefly. The videos of the talks had already been uploaded, so people had a chance to look at it. And if you would like to ask a question, then put it in the question and answer section, just at the bottom of your Zoom. And please make sure that you add the name whom we should ask the question. So we have 5 speakers. So maybe let's start briefly. If everybody of our panelists could very briefly introduce him, herself, and also give a very, very brief summary about the work you were presenting. So I have okay, here's the list also. Maybe we do it in this order. So Claudio, Dorian, Ines, Julie, and then Gan. Claudio, you want to start? You are muted.
Sorry, can you hear me now?
Yes, now we can hear you.
Hi, I'm Claudio Andrea Manzari, a PhD student at the University of Zurich, where I mainly work on flavor physics. Here I presented a talk named Explaining the Cabib-Bengola Anomaly, where I discussed the tension in the first column and first row unitarity of the CKM matrix, firstly within an effective field theory approach, and then discussing some simplified models which could give an interesting solution to this anomaly.
Thanks a lot, Claudio. And next is Dorian.
Hello, can you hear me?
Yes, we can hear you, Dorian.
Always have to check. My name is Dorian Amaral. I'm a PhD student at Durham University at the IPPP. So I gave a lightning talk about how you can explore the U1 L mu minus L tau solution to the now very popular muon's anomalous magnetic moment using potential future experimental probes. And what I looked at with some other people was how things like mu and beam experiments can place constraints on the coupling to this new kind of to this new sector. How spallation experiments can provide us with information about the amount of kinetic mixing with the standard model with this hidden photon, and how direct detection experiments might be able to provide us with some key information on how to disentangle something like an L mu minus L tau from a more generic L mu.
Okay, thanks a lot. Next on the list is Ines.
Hello, I'm Ines Bigaran. I am here a PhD student here at the University of Melbourne, and I worked on chirally enhanced solutions for the G-2 problem in the electron and tau sector and connections of this to different lepton flavor violating models, particularly scalar leptoquarks is kind of my area of study for my PhD here.
So thanks a lot. And then we have Julie.
Hi, I'm Julie Pages. I'm a PhD at the University of Zurich as well. And so in this talk, I presented a model of flavor that is based on a series of spontaneous symmetry breaking at different scale that can explain both the B anomalies, so in the gauge, the extended gauge sectors, and the neutrino masses, which in the first picture, it seems not so compatible with the hierarchical structure in the quark sector as we saw with this anarchy versus hierarchical. And so with this model, we can achieve anarchy in the end, although we start with this U2 flavor symmetry in the quark sector. So we choose U2 to parameterize the quark sector and charge lepton.
Okay, thanks a lot. And finally, we have Ngan.
Hi. Oh wait, everyone see me? Right? Okay. Hi, my name is Nguyen Nguyen, but I also go with Steve Nguyen. So my talk was the result of a search for an axion-like particle in B meson decay to kaon and axion decay into a pair of photon, a per-bar experiment. I'm an incoming PhD student at Johns Hopkins University in particle theory. So some highlight about my talk. So this it was the first search for axion-like particle in the B meson decay. Unfortunately, we didn't observe any significant signal we did improve the coupling constraint of axion particle with the W boson over 2 order of magnitude. And this also proved that the flavor changing decay also can be used as a good channel to look for axion-like particle. Yeah, that's it. Thank you.
Okay, thanks a lot. So originally I was promised a list of questions which is not appearing, so I have to invent. Okay, I got now the first one. So that's to Claudio. The question is, you told us various possibilities to account for the Cabibbo anomaly. Which is your favorite one and why is it your favorite one?
Again, muted, sorry. So, okay, my favorite possibility is the one via vector-like leptons. And the point is that, can you share my slides maybe? Okay, fantastic. Slide number 4, please. Yes, so here I discussed the fact that we have mainly 3 determination of the Fermi constant, the ones from muon decay, the one assuming CKM unitarity, and the one from the electroweak fit. And looking at the plot on the right, you can see that in principle, we always need 2 different effects to bring all these determination together. One moving the red points toward the green, and the other moving the blue one towards the green in the opposite direction. And vector-like leptons allow to do that because in principle, you can extend the standard model with as many vector-like leptons as you want, and you still have a UV complete model, which then can be embedded in bigger and more complex models also. And in particular, we can, we showed that with the triplet coupling to muons, we can obtain the right effect in muon decay, which brings the CKM unitarity, which solves the tension in the CKM unitarity. And with the singlet coupling to electrons, which behaves as a right-handed neutrino in the end, we can also partially solve the problem in the electroweak fit. So let's say we can obtain the most complete solution to this problem, to this tension.
Okay, thanks a lot. When I have a question for Dorian. So Dorian, have people thought about L mu minus L tau in the mu on E experiment?
So I saw this question on Slack from Mathilde, and I've been trying to swat up for the last 30 seconds on exactly what this experiment is doing. But yeah, I have not actually really looked into it. But if I can look into it and I can see if
so all the questions will be put on Slack anyway,
yeah.
And probably there's a possibility on adding it. But there was also a follow-up question to you so that you have something to answer. Do you have models in mind for a L mu model that is not anomalous?
So we kind of focused on the phenomenology of like a generic L mu model. So we weren't too interested in kind of settling on a particular, say, new physics scale where we'd have a particular value for the kinetic mixing in this generic L mu model. So we haven't looked at a particular kind of completion of it that would make it anomaly free, but rather just let it kind of be a general sort of generic model.
Okay, thanks a lot. Ines, you have the bad luck that there was no question for you, so I have to answer a stupid one. So you're introducing these lepton quark models for solving the G-2. Lepton quarks are now extremely popular for discussing the flavor anomaly. So is there any overlap in your model, or this would be it would be purely concentrated on the G-2 anomaly?
No. So yeah. So there is an existing overlap. So the motivation, I guess, for us to look specifically at these chirally enhanced solutions for the G-2 anomaly, both in the muon and the electron sector, was, of course, I guess, primarily because having an anomaly in the electron sector, especially at the time when we wrote this paper, there was a clear anomaly. The electron puzzle has become a little bit more confusing since then because of a new experimental result. But the motivation, I guess, when I first looked at this idea was that many people tacked on the idea of solving the G-2 into their scalar leptoquark models for B anomalies in general, but kind of did a little bit of a rough approximation of how it could possibly solve this particular anomaly on top of the B anomalies that were already there. So I even did that in my first paper. And I guess I was motivated to look into this a little bit more carefully and look more carefully into how easy or hard this could possibly be. And also if this could be extended to perhaps even making predictions to do with the tau G-2 and looking at perhaps hints at some sort of underlying structure in the leptoquark couplings that would allow you to solve more than just the G-2. So the models that the structures that we developed are very easily embedded into existing scalar leptoquark solutions for other B anomalies.
Okay, thanks. When next we have questions for Julie. Okay, this looks more like a comment, Julie. So it's stated, essentially for neutrinos, you're able to fit the data, but you don't really predict masses and mixing as your result is an anarchical neutrino mass matrix. Anything to comment on that from your side?
Yes, so yeah, that's absolutely true. And that's also what Ferruccio said in his talk, that anarchy in a way doesn't exploit all the precision measurement we have on neutrino. But we have a clear prediction from this model, however, which is the PMNS unitarity violation. And this has to be really close to the bounds that we have now. So we could still probe this model via a PMNS unitarity violation test. So by improving on all the PMNS amplitudes, like the angles and also a lot of LFV observables and electroic observables. So there are ways to test it, but yes, we're more solving this issue of the neutrino problem in PS cube originally, and in the end we don't have clear prediction on masses and mixing. We just we can fit the data. That's what you said.
Okay, thanks. For Steve, we have which are the future prospects from Babar? Is this the ultimate analysis from this collaboration? What should we expect from Bell 2?
Hi. I think the Babar, as I said on the talk, although it already stopped operated, the data from Babar still proved to be valid, and then we can use them to look for different like a new particle or beyond standard model physics. And this is just like one of the analysis that ongoing on Babar. So there should be like more analysis, more results coming in next few years. Yeah.
Okay, thanks. So now questions are coming in and we have bigger choice. So maybe let's go back to Claudio. Claudio, the question is, the Cabibbo anomaly is associated to the first column and row of the CKM. What about other columns and row? Is there a similar situation?
No, as far as I know, and maybe there the problem is also about the precision we know those elements, because also, I mean, already in the first column of the CKM matrix, it's true that we have a tension, but we have a much bigger error. Therefore, we cannot still claim for something like what we have in the first row, where the tension is more defined. We already have 3 sigma.
Yeah, I absolutely agree. And for example, top elements were not measured directly, so were only determined by assuming CKM unitarity. When there's a question to Dorian, maybe I'm missing something, but the bounds from NA64 mu are given only for epsilon G over 70. Why the case why is the case with epsilon g over 10, for example, not interesting?
Yeah, so I think especially because such a big emphasis is placed on getting this value for the kinetic mixing, it might seem weird that we don't concentrate on changing it for the Na64 experiment. But the reason is that it's not actually sensitive to that kinetic mixing. So the primary kind of sensitivity to the hidden photon for Na64 mu or any other muon beam experiments is the production, the Bremsstrahlung production cross section, and that's purely dependent on the actual gauge coupling, the G coupling. So it doesn't actually have a dependence on the kinetic mixing. So if you take the bounds that we showed for G over 70 and you close your eyes and then you imagine G over 10 and then you open your eyes, it's the same thing. So because there's no sensitivity, it's the same bounds for both values of the mixing.
Okay, thanks a lot. And one more for Ines. Can you tell us something about the EMDs? So
I think it's meant to say EDMs.
I also thought the EDMs.
Yeah.
Okay, so obviously you can say something about EDMs. Let me just finish the question. Maybe there was something, which is the situation where, what are you willing to explain, letting the phases free? How large are the contributions to the electric dipole moments?
So this is a question based upon something I alluded to at the end of my talk. That was that I'm currently working on extending the model to explain also EDMs in this minimal coupling scenario. And I guess what I can tell you is that it looks as though these types of models, and we're by far not the first people to look into this, but looking at this type of minimal scenario with the couplings as we've described in my talk, it looks like as one would expect, the EDM of the electron is quite constraining on the type of electron couplings you can put in the moment you start putting complex numbers in as your couplings for leptoquarks. But probably more interestingly, the EDM of the muon is it is within the reach of the proposed bounds that are expected to get for experiments such as at PSI. And perhaps they're slightly lower, that it's slightly out of the reach of the G-2 at Fermilab, but it does look like the next generation of experiments could potentially probe these types of models for extending to EDM studies as well.
Okay, great, thanks a lot. And one more for Julie. Julie, how is the hierarchy among the scalar waves explained?
So in the 4D picture, they are not explained. They're just put by hand. But in the 5D picture, and that's what we're working on now, we want to give an interpretation of these hierarchies of Vev through. I talk about it very quickly in the end of my talk through these profiles that have a exponential tail and that connect the different sites together, and that this way you can explain the hierarchies of the Vevs and also the hierarchies of the different mixing that you have.
Okay, thanks a lot. When we have one comment for Stephen on the collaboration, somebody, the name is not given, states ILPs can couple to standard model fermions and therefore the analysis can be much more complicated. The collaboration may consider to take this realistic cases into consideration. Anything to comment on that?
Yeah, so I think, so in this specific search for astronomical particle, in this theory, we can calculate, in our theory, in our theory for astronomical particle, we said that the astronomical particle is like coupled with the standard model boson through a fermion loop. So we're not really like looking for the astronomical particle that they couple with the standard model fermion. So like we can like look specific in this case of the astronomical couple with the boson. So that's what it is, but like I definitely gonna like talk discuss more about this with my colleagues at the Barbara, and they can give more like specific answer in Slack.
Okay, thanks a lot. So we are approaching the last 5 minutes. There are still several questions, so be fast in answering it. One is for Claudio. And the question is, you have written the scale for new physics for various decays. How do you determine this scale?
Okay, so in principle, in all the processes we considered, in each of our simplified models, the new physics and effect enters as coupling squared over mass squared. Therefore, we can set limit on this ratio, assuming then, for example, that we want to be in the perturbative regime, and so our couplings cannot be much greater than a few units, then performing a global fit to all the observables, which are, of course, the ones we are interested in, the one constituting the Cabib-Bengola anomaly, and in particular the electroweak fit, we can estimate some lower limits for our new physics scales, which usually are at the TeV level, below TeV only for vector-like leptons, where also the experimental constraints are lower. So we are fine with them.
Okay, thanks. Then one more for Dorian. Dorian, could your Z prime be useful to explain other anomalies?
Yeah, so this is an exciting question, and I know we're running out of time, but can I quickly bring up my slides? Oh, look at that, you're ready. I think like maybe slide 5, I'm guessing here. Wait, stop, slide 6. Yeah, this one. So someone on the Slack yesterday was posting about the new physics models to explain the H0 tension. So an L mu minus L tau, or indeed I think just an L mu, this kind of new hidden photon could actually reconcile the tension between early and late time measurements of the Hubble H0. I think by basically changing the number of effective neutrino species that you'd get very early on in the universe. So this blue band in this picture over here is where, so you need a particularly light hidden photon, but this blue band here kind of represents where you could reconcile the late and early time tension in the Hubble parameter. And then this kind of like little square in the middle is a kind of very seductive region where both the mu on G-2 and the H0 tension could be resolved, which is where our BP1 lies. So this is kind of the most exciting region to look at in this landscape.
Okay, thanks a lot. And one more for Ines. I see you have bounced from KL to EE. I'm wondering if you also have predictions for flavor diagonal processes like Pi0 to E plus E minus. This mode was measured at KTEF and is in tension with some standard model predictions. Any comment on that, Ines?
So for this one, in both models that are looked at in my paper, we actually don't have a direct coupling between the down type quarks and the charged leptons. And we switch directly off the up quark electron coupling. So the leading order contribution to that, I believe, comes via a box diagram and is extremely suppressed. So we aimed to give a very minimal coupling scenario. So we turned on the minimal number of couplings to give basically people a structure to aim for, or a structure to embed in a more extended model. So I would guess an extended model that embedded this type of structure would be able to give a prediction, but not in this particular case.
Okay, thanks a lot. So unfortunately, time is running late. So sorry, Julie and Steve, for not getting an additional question, but I think we have to switch to the poster session. So thanks to all of you for this interesting panel discussion. And now the poster session will take in, how is it called? Gather.town. Yes. And you should find the link somewhere in the WIN bulletin emails that were sent to you. Okay, so thanks from my side to all of you, and hope to see you all soon in real life at the real conference where we can meet again. Bye.